Okay, so this is the last section in chapter 4. It's a very short section, and in this section, we're going to describe two factorization algorithms. First one is given by Fermat, and we're going to start with describing this algorithm, and we're going to present some examples using Fermat's factoring method or algorithm. Then there is an improvement for Fermat's factorization algorithm given by Kraitchik, Maurice in the 1920s. And we're going to give a description of this algorithm as well and look at some examples to illustrate how actually the algorithm runs. All right, so let's get started with Fermat's factorization algorithm. Fermat's factorization algorithm or method is based on the following theorem. All right, here it is the theorem. And it is stated that let n be a positive integer. Actually, we want it to be odd because if it is even, this is very simple. Be an odd positive integer. Then there is a one-to-one correspondence, a one-to-one correspondence between the factoring of n in this form n equal AB, where A and B are positive integers. Of course, they must be odd positive integers. And this actually includes the trivial factorization in case n is a problem, which means n is going to be, A could be n and B is 1. All right, so assume A is a bigger one. Okay, so all these are positive integer, and the representation. So this is what the correspondence between the factoring of n in this form and the representation of n as a difference of two squares of this form. Form n is equal x squared minus y squared, where x bigger than y or n. Again, let me say positive integers, even we are squaring these are positive. All right, this correspondence actually is given by this. This correspondence is given by this. If n is equal AB, then we take the x, but corresponds to this is a plus b over 2, and y is equal a minus b over 2. So we are assuming in here a is actually bigger than or equal to b, both bigger than 0. Okay? And the other way around, that is if n is a difference of two squares, then the a is going to be x plus y, and the b is going to be x minus y. Again, we are assuming in here the x is bigger than 1. All right, let me put them in here. All right, we're going to go ahead and prove this theorem. Now, before we kind of go with the formal proof, you can see if we can express n as a difference between two squares, then we can factor this difference between two squares, and then we have x minus y, x plus y. And if it happens that this factoring to x minus y and x plus y is not trivial, means x minus y is 1 and x plus y is n, then we have actually a proper factorization of that. We're going to see that the method we're going to use to express n as a difference of two squares is going to lead to a proper factorization or show that n is in fact is a problem. All right, so either way, we're going to be able to determine what would be the fate of n, as well as if it is, of course, composite to calculate. However, this is not an effective, okay, or efficient algorithm to show n is a prime, because it's going to take many steps, as we're going to see from the algorithm, to show that n is a prime. So there are pseudo primes, or primality testing based on pseudo primes are more efficient. All right, here's the proof. So there are two things that we're going to show, and actually both of them are pretty straightforward. So let's assume that n is equal AB, where A bigger than or equal B bigger than 0, or positive entities. Now, since n is an odd integer, sorry, positive, then both A and B are odd. Cannot be either one of these is even, because then we have a factor of 2, and the other part is going to have a factor of 4. All right? Now, this implies that A plus B and A minus B are both even. Now we're going to let x equal A plus B over 2, and y equal A minus B over 2. These are integers. So each one of these is even, so we can divide by 2. All right? Moreover, when you take the x squared minus y squared, which is equal A plus B over 2 squared minus A minus B over 2 squared, and you work this one out, and you square this, so you get A squared plus 2AB plus B squared over 2, and minus A squared minus 2AB plus b squared over, anyway, this is over 4. Over 4. And when you subtract, you get the a squared cancel out, the b squared cancel out, and you come up with 2ab plus 2ab. So you get 4ab over 4. This is ab, which is equal to. Oh, so these values of then if we take the x is equal to this, the y, then the difference actually is, or n, we can write it as the difference of 2 squared. The purpose of this is the same, all right? So other way around. Going this way, if n is a difference of 2 squared, then n is equal x minus y, x plus y. Then we're going to let a equal x plus y, b equal x minus y, then a bigger than or equal, so it's going to be probably strictly bigger than b, and both of these are positive because we are assuming in here x is bigger than y, bigger than 0, okay? So actually this one is being greater, so we get this. And we are done. Means we were finding A and B. Oh, one other thing, of course, here, because in here, then we have, of course, AB is equal. All right, so now the question is, how we can find x and y so that n is a difference of 2 squared. Okay? So we write the question, and then this is what the steps of the algorithm, it's going to actually give us the values of x and y. All right? So the question is, how can we find x and y such that x squared minus y squared is equal to n? This is the way we proceed, all right? We start with actually the lowest value of x, which makes the x squared minus n is a square, all right? So we're going to start with the, by this value, we start with x1 to be the greatest integer of the square root of n plus 1. All right, so this is the basically the integral part of the square root of n, because it is, of course, positive. You just take the integral part and add 1. Then we calculate this number, which is x1 squared minus n. Actually, let me do this one in steps, okay? So, so this is the first one, all right? So the second step, we take this one in here. So step number 2, we calculate x1 squared minus n if this is a perfect square let's say y1 square, that's equal to y1 square, then we have x1 square minus n is equal y1 square. And this gives us n as a difference of 2 square, and we are done. And we stop. And if it happens that then x minus y1, let me put this plus y1 in x1 minus y1 is a factorization of n. Now we hope, of course, unless n is a prime, then we got to hit on a square immediately. Then this is it. Either it's going to be a proper factorization or it could be improper factorization. I mean, this is n and this is 1. And this is actually true if you take n, for example, is equal to 3. All right? Then that's what you end up with. Otherwise, if, on the other hand, if x1 squared minus n is not a perfect square, or just a square, then we go to step 3. To step 3. All right, step 3, we're gonna take x2 to be x1 plus 1. So we're gonna increment x1 by, so step 3, so we're gonna let x2 equal x1 plus 1. Then calculate x2 squared minus n if this is a square. Let's say y2 squared is equal to x1 squared minus n, then 2. Then we have, in this case, again, x2 squared minus n minus y1 squared is equal to n. Then we continue this process. And I claim that it will stop. So we repeat. We repeat step 3 until we get x sub k to be actually bigger than or equal n plus 1 over 2. So in this case, where xk means after k steps, basically, xk is equal to n plus 1 over 2. Then in this xk squared minus n is going to be n plus 1 over 2 squared minus n. Well, let's calculate that. So this becomes n squared plus 2n plus 1 over 2 over 4 minus n. All right. And this becomes n squared plus 2n minus 4n. And this is equal n squared minus 2. Oh, we need a plus 1. Sorry. Plus 1 minus 4n. So this becomes negative 2n plus 1 over 4. And this is equal n minus 1 over 2 squared. So in other words, when we have and this is a perfect square, so this is y sub k squared. And this leads to a trivial factorization. So this becomes x k, we're going to take it as n plus 1 over 2, and the yk equals n minus 1 over 2. And this gives xk squared minus yk squared is in fact equal to that. But the factoring that we obtain from here is, of course, the trivial one, as we will see. And then we end up with n is a prime, because if this is means the value we have to reach, all right, and we have the n plus 1 over 2 squared minus n minus 1 over 2 squared. This is equal n plus 1 over 2 minus n minus 1 over 2 times n plus 1 over 2. We make this is the plus and make this is the minus, n minus 1 over 2. Well, this one is going to give you n, and this one is going to give you 1. So this is the trivial factorization. And in this case, again, this is actually n also, all right? And in this case, n is a prime. But either we end up with a proper factorization or we end up with n is a prime. Let's look at an example. To illustrate both possibilities, when we get a prime and when we have a proper factorization and when we get a prime. All right? So the first example I want to look at is n is equal to 4,890. So let's look at the first example. And 4,800. So the first thing we would like to look at is the square root of this. So remember that we're going to start with x1 is the square root of the greatest integer function plus 1. And the square root of this number happens to be approximately 69, or this is 69 plus 1, so this is 7. And so this is the smallest value where I go that. Now, the largest value of x is going to be x sub k, we call it, and this is going to be n plus 1 over 2, which is 4,820 divided by 2. This gives you 2,410. So in other words, our x values, so we're going to try the x values to be between 70 and 2,410. So as you can see, there are actually many, many values we have to try in here. So to show that n is a prime, okay, means if we think of this, then we have to do these calculations many, many, many steps. It's basically the difference between these two values, right? And if n is very, very large, you would imagine that n plus 1 over 2 is going to be very large. The square root is okay a little bit, but not the largest value. All right, now we can do this calculation making a table till we get into a square, and then we stop. And then we have a factoring at least of n. Now the factors we obtain, they might not be primes themselves, and then we, of course, we could repeat the procedure. So if we make a table of values in here, actually it turns out, actually this is the way it works, but in general, so this is the x sub k, and then we have in here the x sub k squared minus n, and let's see here. So we start with 70. So this is 70 squared minus the number itself, which is 4819. And this happens to be actually is 81. All right. So, and this is a square, so this is 9 squared. Now we are done. Other than this, if it's not a square, then we're going to go to 71, 72, and so on. All right. So we're lucky this time. So we can take the x to be 70, y to be actually 9, and we have x squared minus y squared equals 70 squared minus 9 squared, and this is equal to the number itself, 819, and it happens that less than 70 minus 9 is the proper factoring, and this happens to be 79, and this one is 61. And we can check this, and both of these are primes. So both these are primes, and so we have the prime factorization of 4,890. All right, from what the first step. All right. Let's look at an example where we will actually run it through all the values and end up with the number to be a prime. So let's take n to be 31, which we know it's a prime. So we know this is a prime. And let's see what the procedure or Fermat's algorithm gives us. So it starts with x1 square root of 31 plus 1. And 31 is about 5, plus 1 is 6. All right, and the largest value is going to be the 31 plus 1 over 2. That's equal 60. And we're going to make the table of values in here, and we're not going to see a square till All right, so we start with 6, and so this is 36 minus 31, and this is 5. Let's go with 7, and this is 49 minus 31, and this is 28, yes? 0 or 18 rather. Subtract. Of course, I don't want to go through all of these, but you're going to get the square when you reach actually 16. So this is 16 squared minus 31, and this happens to be actually equal 225, and this is 15 squared. And so we take the x is equal to 16, and the y is equal to 15, and we have the 31 is, of course, is equal to 16 squared minus 15 squared, which is 16 plus 15, that's the difference of square, and this is 16 minus 15. So this gives us 31, and this gives us 1. So you get the trivial factorization, which means that 31 is upright. All right. We look at another also example where we need more than one step, and then I want to look at an example that actually Fermat himself worked. An example that he used his method to solve. So here's an example 3. Mistake n is 7, 7, 9. And again, the x1 square root of 7, 7, 9 plus 1. This is going to be 28. And the largest value, it's large, maybe put it differently this time. This is going to be 7, 7, 9 plus 1 over 2. This gives me 390. And for the table in here, turns out actually after 2 steps, we get this 28. So this is x squared minus 7, 7, 9. This gives me 28 squared minus 7, 7, 9. This is equal to 5. Then 29 squared minus, and you see this is increasing the sequence, and this becomes 62. No, actually after 3 steps. And then we have 30 squared minus 7, 7, 9. It happens to be equal to 11 squared. All right, so this is the y, and this is the x, and then n. You're going to see it is x plus y. The y is actually just the 11, okay? So y is just the 11. So it's going to be 30 plus 11, then 30 minus 11. 41 times 9. All right. The example that Fermat actually took is a much bigger number than the example I worked on. So let's see what it is. And now remember, Fermat does not have a calculator to use. You have to use hand calculation. And he was patient enough to go through all these steps. So this is Fermat example. That's the one he did. And this is the n. It's 2, 0, 2, 7, 6, 5, 1, 2, 8, 1. All right, big number. the square root of this, it is approximately equal or x1, and we put it with x1, which is this, plus 1, turns out to be equal to 45030. All right, and x large, the largest value we need to check is 101, which is the sum of this number and 1 divided by 2, 3825641. This is n plus 1 over. All right, so it took Fermat 18 iteration, 18 steps to get to a square. So the xk squared minus n, and started with 45030. It gave this the difference, 99944. And after 11 steps, so we come up with 45041, and the difference is this. And this happens to be in 1020 squared. So using the this is the x, and this is the y. He found that the factoring of the n is equal to the product of 46061 multiplied by 44021. That's a lot of work. Even with a calculator, if you want to do these calculations, this is squaring and checking if the number you get is actually a square or not, it's a lot of work. All right. Now, of course, these methods nowadays can be programmed easily, and you can do this. But wait, for relatively small numbers, for very, very, very large number, again, the number of steps is too many. All right, to carry this in practice. All right, so this is Fermat's method. One thing about Fermat's method, when it works better or it is efficient, when the number of steps here, all right, is not going to be very many, right? And this happens actually if n happens to have two factors are close to each other. Okay, so when the the numerical value for the two factors x and y are close to each other, then we obtain a factorization in a relatively in a relatively short amount of time. However, how do we know that? We don't know. Okay, just this is efficient when the x and the y are close. Now, Kraitchik, back in the 1920s, actually improved Fermat's factorization method by, instead of looking at actually two integers x and y, such that the difference between them, the square of the difference between them, is equal to n. So this is what the Kraitchik actually did. I hope I'm pronouncing the name is correctly. It's a Belgian mathematician. Okay, this is in the 1920s. All right. So in Fermat method, we need to obtain x and y. Remember, this is the method, regardless how we parameter these, such that x squared minus y squared is equal to n. Now, Kraitchik suggested to obtain x and y such that x squared minus y squared is congruent to 0 mod n. Or equivalently, that x squared minus y squared is a multiple of n. Instead of equal n is a multiple of n. All right? Well, this congruence right here, we also can express it as saying that we are looking for x and y such that x squared is congruent to y squared mod n. All right, the question is how we would use this idea to actually do or find the factoring of n. And that's what we need to discuss, you know, where I'm going to use the x and the y themselves, all right, but we're going to use actually the greatest common divisor of, you know, expression using x and y. And so this is the way the method works. First of all, so this is what our hope for. Okay, so this is the main idea. Find x and y such that x squared actually is congruent to y squared mod n. Now, there are two trivial actually solutions for this. There are two trivial, what we call them, all right, the trivial integers, x and y, that satisfy the square congruence. Namely, x is congruent to y mod n. If this is true, then when you square this, means you multiply by itself, you come up with that to be correct. So if this actually does hold, all right, and the other one is x is congruent to negative y mod n. Or y is congruent to negative x, doesn't make any difference. In this case, we have the greatest common divisor of x plus y. We start with x minus y, correspond to the first one. N is equal to 1. All right? Because in this case, what we have from the first one, n divides x minus y. And this one, it gives us the greatest common divisor of x plus y, n is equal to 1. Again, because n divides x plus y. However, if we exclude these solutions and we find x and y that does not satisfy either one of these, all right, then it turns out that the greatest common divisor of x minus y and n is going to be bigger than 1. And the greatest common divisor of x plus y and n is going to be bigger than 1. And then we have actually a factorization of n. Okay, so let me write this information down. Okay, so if we can find x and y such that x is not congruent to plus minus y mod n, where n we know that n is composite. We're going to start with a number that is composite. We don't want, and we know there are, we could use Fermat's theorem to show it's a number is composite, and then we see its factorization, and we could proceed with this method, okay, where n is the prime. Then we have the claim that the greatest common divisor of x plus y n is bigger than 1, and greatest common divisor of x minus y n is bigger than 1. And now since then we can see that actually this implies that the greatest common divisor, if I call it D, all right, in either one of these cases, then we have D divides N, all right, and D. Let me call this is D1 and D2, D1, D2, and D2 divides N. All right, so, and hence, we have proper factors of n. All right. Before I prove this claim, let me look at an example, and then we can go ahead and prove this claim. All right. Here's the example. Let's take n to be 4,633. Then x equal 118, y equal 5. They actually satisfy the quadratic congruence. X squared is congruent to y squared mod 463. Let's check. So since t squared minus 5 squared is equal to 13899, and this happens to be 3 multiplied by 463. So yes, it does actually, as you see, divide. So this means that 118 square minus 5 square, the number 4633 divides them. So it satisfies the congruence. Moreover here, when you look at the greatest common divisor of the sum of the x, which is 118 plus 5, and the number itself, and this turns out to be equal 41, and the greatest common divisor of the difference this is equal 113, and this divides the number, and this divides the number as well. And both of these are primes, and their product is actually the number itself. So, and we have the product of 41 multiplied by 113 is equal 4633 is the prime factorization. Because both 41 and 113 are primes themselves. Now, of course, the big question is, how magically we came up with these? Well, that is what actually the Kraitchik algorithm is supposed to do, is to give you these values. All right? Now, Kraitchik himself, he probably used actually a more or less a, trial and error method. Or the way we're going to kind of look at the possibility that he actually did use. Now, it turns out that this scheme that actually Kraitchik used, okay, later on in the 1970s and 1980s, some of the powerful techniques of factoring actually build upon this idea of Kraitchik. Means trying to come up with X and Y, okay, using different techniques, okay, and then calculate the greatest common divisor, which easily can be done using the Euclidean algorithm. Two of these methods that actually uses this idea of Kraitchik, okay, called Kraitchik scheme, is the continued fraction method developed in the 1970s, and then another method called the quadratic set, okay, algorithm or method. It's actually introduced in the 1980s by Karl Pomerantz, okay. So we're not going to go through these, but these are some of the actually reasonably efficient, okay, methods for factoring, and they are actually used in practice nowadays. All right. So the idea, first of all, let's look at the proof of the claim. And then we're gonna outline how we could come up with the values of X and Y. All right. So the idea is this. Okay. Now remember that to prove the claim, so we have X squared is congruent Y squared mod N. So assume that we have X and Y values such that this congruence is true, and we want to assume that X is not congruent to plus minus Y mod N. Now from here we obtain that this implies that N divides the difference between these, which is X minus Y, X plus Y. But since X is not congruent to plus minus Y, this mod N, this implies N does not divide either one of the X plus Y or N, actually and, not or even, and N does not divide X minus Y. So we have now this, N divides x minus y, x plus y, but n does not divide x plus y, and n does not divide x minus y. Well, this means that n, which we know it's composite, is equal n1, n2, where we have, and let's assume that n1 is bigger than n2. Then this n that divides the product is coming from n1 and n2, which means that n1 is going to divide x plus y, and n2 is going to divide x minus y. All right? And which makes that the greatest common divisor for the x plus y is going to be actually bigger than or equal this n1, at least bigger than or equal 1, right? And so this implies that the greatest common divisor of x plus y and n, this is going to be bigger than or equal n1, and greatest common divisor of x minus y, and is going to be bigger than or equal n2. In particular, if n is a product of two primes, PQ, where P bigger than Q are primes, then the greatest common divisor PQ, remember PQ in here, which is n, is going to equal actually the larger prime, and greatest common divisor of x minus y, PQ, is equal to Q. Because remember that the greatest common divisor of a number where PQ is going to be either 1, PQ, or PQ. And we cannot have 1 or PQ, all right, which is in itself, and then we end up with actually this, all right? All right, let's look at actually an example, or the procedure actually we follow through an example, all right? And then we can actually write the steps of the algorithm as we move along. All right? So here is the example. State n to be 18601. So first we define, so this is step 1. We define the Q of x to equal x squared minus n. All right? And we let x sub 0, like we did with the, or a slight modification in here, maybe just the greatest integer or the square root of n. So in this case, it happens to be the greatest integer of 18601, and this is equal 136. Then we, next step, we're gonna define a sequence of x values by x sub k equals x sub 0 plus k, for k equal 1, 2, 3, and so on. And then step 3, which we're going to calculate the q of x sub k. All right, for different values of k. All right, the next step, I'm going to wait on it till we do some calculation in here, all right, for this particular case, and show you what the fourth step it will be. All right, so let's do this. We're going to make a table as we did before, but this time we're not going to end up with the x value and the y value from only one of these calculations, okay? So that's the difference. So in here, we make in this table the, actually also we need a value for k. So this is k, this is xk, and this is the q of xk. And remember, this is xk squared minus the n, which is 18601. All right, so the first K1, then the number is 137. And this becomes, actually, when you plug this one in here, minus 18601, turns out this to be equal 168. Now, 168 is relatively small number compared to the original number. And then we're going to do a prime factoring of this, okay? The prime factoring of this. And that's where, you know, this newer method actually is kind of having a, you know, an effective way of doing this, or all right, so this is prime factors or factorization of q of xk. All right. The next time k equal to 2, this becomes 138, and when I square, I come up, when I do the calculation in here, I end up with 443, and this is a prime itself. So this is 443. So no proper factorization. Then when n equal to 3, this is 139, and this becomes 720, and we end up with this 2 to the 4 times the 3 squared times 5. Then we're going to go with 4, so 140, and this becomes 999. And this factors to 3 to the 3rd times 37. Then we have 5. And as you see, none of these is a perfect square there at the very last, you know, column in here. And then this one, 1280, and the factoring of this is 2 to the 8 times 5. Now, what we're going to do here, we're going to try to find, you know, from here, a number of x's, not necessarily one, to form a square, all right? So this one and this one, no, this one and this one, if you put them together, you're going to have 2 to the 7th, okay, and that's not going to give you a perfect square, 7 and 5. However, when you look at this one and the last one, all right, if you put these together, it gives you a perfect square, all right? So there's 2 to the 4th times 3 squared times 5, and 2 to the 8th, 5, give you a 2 to the 12th times 3 squared times 5 squared. So this is a square of 2 to the 6th, 3, and 5. Now, this is what we take as our y, together with the x is going to be actually the product of these. So this is the x. It's going to be 139 times 141. Well, let's actually see this, okay? In other words, y actually does this work. First of all, let's see it does work here for these numbers. And then we will present the justification for the in general. We take all this out here, and I'm going to take all of this, just leave the x and the y. All right, so now I'm saying that this x squared minus y squared, actually we say x squared is congruent to y squared mod the number, which is 18. Where's the number in here? 1860. We're going to check if this is actually the case. So this is 139 times 141 squared. Is this congruent to the y squared, which is 2 to the 6 times 3 times 5 squared mod 1860? This number right here turns out to be actually 960 squared. And this number in here is, I don't know if I have this product. Actually, I don't have this product. But it's going to leave it for you to actually check and see if this actually works or not. This is congruent to mod this number right there. Now, once we have this, then we calculate the greatest common divisor of the x plus y, okay? So we take actually the, so this is the x, and remember this is the y. So we're going to take the sum of these, and it turns out that the sum is 998. That's the product in here. So this product is 998, all right? And 998 plus 960, and with the n 18601, it turns out this is 979. And if you calculate the greatest common divisor of the difference, 18601, this is a much smaller number, 90. So we got that these are factors of n. All right. Now, why this works? Why, actually this works? So let's look at again at this example, and then it would explain the method in general. Now, so what we have an x, one of the x's, all right? Let me actually take the x, I don't know which number it is, but I will write it. Let me look at my notes here. We found that the x3, which is 139, okay? And then we have the q, what I call the q of x3. This happens to be equal to this number. And we have, the q of x3, which is equal 139 squared minus the n. Let me just write it as n, okay, which is 18,601, all right? Now, I know this one is equal to 720, all right? Well, I can write this as actually a congruence relation. So this becomes congruent to each other mod n. Because the difference between these is 139 squared, actually minus 720 is equal to n. All right? So it's congruent there. And this is the case for all others. So for the x5, this is equal to the qx5 is 141 squared minus n. All right? And this happens to be, when we did the calculation for this, is 1280. And again, this makes the two numbers that this is congruent to each other mod n again. Right? Because the difference between them is n. Now, when I multiply, all right, the x's, which is x3, all right, and the x5 is squared, all right, and this is going to be actually congruent to the y's that I got from these, because in y1 and y2 is square mod n. Once I found them as square, then I can claim this. All right? So the idea then is to make a table and try to catch or find among the prime factorization, if you can combine them to come up with all the powers of the prime that appear in the prime factorization for the different values in the table to become a complete square. Now, once we have this, let me just make the justification in general. Okay, so let's say we obtained so let's assume we have the following. Okay, assume that we have values of x, say, or x case, let me go there. Let's say, now all of them is going to be x k sub 1, x k sub 2, and so on to x k sub n. All right? Such that when I multiply the q of these, k sub I equal 1 to m, all right? When which is this, what this is equal to is the product of I equal 1 to n x k sub I is square minus n, that's what the Q. And this happens to be a square. Okay, so we are getting a square once we collect, some of these x's. Okay, then I claim that this give you the product of the x's, which is x k1, x k2, up to x k sub m squared is congruent to y square mod n. Okay, so we're going to prove this claim, why this is the case. Okay, and the reason for that is the following. We have these all right. This one is, of course, is congruent to x k sub I square mod n. Because it is the same number with a mod, it's n itself, so we just, if we take mod, we get this one. Now, once I do this, the multiplication with all these different congruencies, all right, so I get y squared is going to give me, when I want to multiply all of these, xi squared minus n, and this is going to be congruent just to the x's. Again, I equal 1. So this is true for every I, okay, from 1 to m. And in this one, which is the same as actually pi, I equal 1 to m, xk sub I, xk sub I, quantity square. So instead of, square all the numbers and multiply them, and the square the result. And all of this is congruent to mod n. And yes, we do have the claim that the product of the x's is congruent to I squared. And then we use the greatest common divisor, and that's it. All right. Let me look at one other example. All right, again, to illustrate this one more time. Just to do pure calculation without going through details of the explaining why this works. All right, so the number I'm taking this time is this. Again, the x sub 0 is the number not adding the 1. You're going to add 1 to the different case. This happens to equal 142. All right. So we make a table. So this is the K, and this is the Q, x sub K, which is x sub K squared minus n. And actually, this is the result in here, and we're going to put the factoring here. I'm factorizing. And this is equal. All right, 1. See how many I need. So you're going to start every time you do one calculation, you're going to see if you get a square. 3, 4. Surely this is there. Actually need the 3. So the first one is going to be the x in here is 143 squared minus n, and this is going to give you 12. And the factoring of this is 2 squared times 3. Then with 2, we come up with 144 squared minus n, and this is equal to 99, and this is 13 times 23. Then 145 squared minus n, and this is 588. And this happens to be 2 squared times the 3 times 7 squared, and we are done. As you can see, these two form a square. We have 3 to the 4th, 3 squared, 7 squared. So our x is going to be the product of the 143 and 145, and the y is equal to these without a square, so that's going to be equal. In here we have 2 to the 4 times the 3 squared times 7 squared. So we're going to take 2 squared, and then the 3, then 7, and this all together multiply to, let's see, what does this give us? 84. Then we calculate the greatest common divisor of the sum and the difference between these and n. Okay? So from here we calculate the greatest common divisor of the sum of these is going to be equal to, let's see in here, 20, which is this number right here, is it 2735, all right? So 2735 plus 84 and n. This happens to equal to 191. And the difference, 2735 minus 84 and n, in this it turned out 107. And when you multiply this out, actually it gives you the number that we are factoring. Okay, so these are the 2 prime factors, and we are done. All right, let's stop right here.